All right. Okay. Hello, everybody. Welcome back to Comp 3430 Operating Systems. Iteration 2 is today or tomorrow? Tomorrow. Okay, tomorrow. Okay. Why would you show up if the class is optional? I am so happy to see you all here. I am so happy to see you all here. Thank you for coming. Thank you for coming. Yes. If your first class was optional, I'm really delighted that you're coming here. Thank you for coming. I hope that you're all doing good today. Today, what I want to do is focus on virtual memory. So last class, I stepped through some of these, and I'll step through them again quickly to remind you of what we're thinking about. But the basic idea that we're looking at today is I want you to be able to explain how a process's entire address space can be provided by the concept of virtual memory. So we're going to look at this from a couple of different perspectives. The first perspective that I want to look at this is, what does an address space look like from the perspective of a process? What does a process actually see? How big of a range can it address? What are the addresses that a process is able to deal with? And then how do we take that idea and then cram it into physical memory? And that then is starting to think about how an operating system might work with the underlying hardware to manage this idea of virtual memory. So with this giant address space, or in some cases, this actually quite small address space, last class, we sort of discovered that our operating system really cannot be responsible for translating these virtual addresses into physical addresses, just because it's going to take lots of instructions to even accomplish that. And so we need our hardware to be able to help us with that. And so we'll take a look at a couple of different approaches to how an operating system and then different variations or different versions or iterations of hardware have changed over time to be able to support this idea of virtual memory, and what an operating system needs to tell the hardware, this is what you need to do to translate these addresses for this process into an actual physical address. All of the mechanisms that we're going to look at for virtual memory require either partitioning the memory itself, physical memory, into smaller pieces. The word partition here means I'm going to take this big thing and I'm going to break it into smaller pieces. In the cases that we're looking at, the smaller pieces are generally going to be fixed in size. They're all going to be the same size, and they're all going to be fixed in size when the system comes up. All kinds of virtual memory are either going to do partitioning physical memory, partitioning our address space, or doing both of them at the same time. So splitting everything up into smaller pieces. Ultimately, I'm also looking for you to be able to compare and contrast these methods for address translation. So we're going to take a look at three different approaches. One is base and bounds, one is called segmentation, and the other one is called paging. And I want you to be able to describe effectively how one solves problems that the other one has. So how does paging ultimately solve problems that segmentation had? How does segmentation solve problems that base and bounds ultimately had when we were stepping through that? If we have some time, I would like to start taking a look at this idea of thinking about what's going on in different parts of our system as the words segmentation, fault, core dumped are being printed to our screen. And I can see people's eyes twitching here already. Just seeing the words is enough to trigger you. We're going to think about this idea of what's actually happening underneath all the different parts of our system when that's happening. All right, so first and foremost, I kind of want to place us in terms of where we are right now in the context of the course using something called the memory hierarchy. Has anybody seen this shape anywhere before in the context of a computer science class? Nobody's seen a triangle before, but yeah. Have you seen this idea of memory hierarchy before in Comp 2280, maybe? It's okay. It's super okay if you haven't. The memory hierarchy here is a visual representation of the structure of memory that we've got in a computer system, and it kind of describes different properties of the different types of memory that we've got in a computer system. This is starting to step again on the toes of Comp 3370 computer organization, but we've actually touched different parts of this memory hierarchy throughout this course already. At the very beginning of the course, we were starting to talk about file systems, and that's at the very bottom of this triangle shape. The very bottom of this triangle shape is effectively saying these are the largest capacity types of memory. These are long-term storage, they last for a long time, and the cost per byte or the cost per gigabyte is really, really small for these things. So I can buy a tape drive, or now I can buy hard drives where I'm getting to the point of terabytes are a few dollars or tens of dollars to have a terabyte worth of space on a disk. This is where we started at file systems with kind of like power off stuff, going all the way up into flash and USB memory. So exFAT is a file system that you might commonly find on USB drives now. This is something that we would put there, and it kind of saves memory for the long term. When we were starting to think about processes, and then when we started to think about threads of execution, we're now starting to touch on the very top of this triangle. And at the very top of this triangle, the context here is this idea of a processor control block, a process control block, a thread control block, the state of the processor. What is the program counter right now? What's the stack pointer? What do these registers have in them as I do context switching? At the very top of this triangle, these are the fastest kind of memory. Each register that we've got is maybe 64 bits or 128 bits, or it might be bigger than that, or it might be smaller than that, depending on the register that we're thinking about. But the cost per byte here is exorbitant. It is crazy high because they are so fast. We're talking about like nanosecond level of access times here. It has to be super, super fast, and it has to be physically close to the processor so that even the speed of light, distance from one location to another on the main board of your computer is not affecting how much time it takes to get things into these registers. So they're very, very fast and very, very expensive. And that's where we were when we were thinking about processes and thread control blocks to some extent. We're not going to talk about processor cache in this course. This is something that you will talk about in detail in Comp 3370. There are chapters in our textbook about this idea of processor cache, including things like the translation look-aside buffer, which is something that I'm going to say right now and then never talk about again, because you can take Comp 3370 if you want to learn a little bit more about that. But the processor cache is something that you might see described on processors as there's 3 megabytes of cache on this system, L1 or L2 cache on this system. The place where we are right now, though, is this part, the random access memory part. We're going to be thinking about virtual memory, and virtual memory ultimately is a way for a modern computing system, both the operating system and the hardware underneath, to work together to make it seem as though processes that are running, code that's running, has access to a really big address space, where in reality, it's actually only using a tiny little bit of memory at runtime as it's going. So the place where we're at in this is we're kind of in the middle of this, this computer memory hierarchy right now in terms of the computer memory hierarchy. Related to the computer memory hierarchy, there are some other triangle-shaped things that I thought were important to bring up here. Bloom's taxonomy is something that I think a little bit about as I'm kind of going through courses and trying to design assignments and stuff. This is a tool that teachers and instructors will use to try and help place learning outcomes. So describing what you should be able to do and how you will be assessed on that thing. At the very bottom here is comprehension and knowledge. And this is a lot of stuff that would be like, I want you to define this term, to describe this term to me in a written test. The place where we're at in this course is more like application and analysis, so kind of in the middle of Bloom's taxonomy. So here we're taking a lot of the concepts that we're thinking about, like scheduling policies, and we're actually writing software to build these scheduling policies. To some extent, you're doing analysis in terms of thinking about how these scheduling policies apply to different workloads. As you get into 4,000 level courses and grad courses, that's where you start to get into evaluation and synthesis. Synthesis is where you're like, I'm actually taking all these different ideas and I'm making something new that nobody has ever made before. Analysis is then taking these new ideas and starting to think about, evaluation is starting to think about how that fits into the bigger picture. Another triangle-shaped thing is the pyramids. These are in Egypt. I would really love to go here someday, but I don't think that's going to happen anytime soon for me. My kids, I don't think they could deal with transatlantic flights at this point. So if I am going to go see the pyramids anytime soon, I'm going to be leaving them at home. But I'd really love to go there someday. There's also that pyramid-shaped thing on top of the US money and US currency that shows up. There's the Bermuda Triangle. This is kind of this famous place where planes and boats kind of get lost. And then finally, there's the flag of Nepal, which is an excellent kind of landing point here because it has two triangles in it instead of just one. Nobody's laughing. Like, that was supposed to be funny. But maybe that's just where we are right now in the course. Maybe that's just where we are. Let's talk about virtual address spaces. For the last several years, I have told you, not necessarily me directly, but other instructors that you might have, and then me now have told you, code heap stack. And we've told you this over and over again, that this is the way that the program's address space looks. So in Comp 2160, we tell you about the code section and the heap section. When you're doing malloc, you're putting stuff in the heap section, and there's this stack that lives at the bottom, but we don't really spend too much more time talking about it than just verbally saying this is what it looks like internally when a process is running or when a program is running. I want to be able to make observations about this. I would like to run a program, and I'd like us to be able to actually see that the program's code section is somewhere at the top of the virtual address space for this running program. I want to see that the heap is somewhere beneath that, and I want to see that the stack is somewhere at the very bottom of the address space that we've got. So I want to do that in two different ways. The first way that I want to do it is by running some code. I welcome you to clone this repository and follow along with me if you have a Linux system at your disposal, or if you want to run this yourself on Aviary so you can see it a little bit bigger than what's on my screen. But I'm not going to modify this code. This is code that's already written. I'm just going to run it. I'm going to step through what each of the parts are doing, and I want to observe the outputs of this program itself. So I'm going to switch over to my terminal here. And I actually already have this, this program open. This program doesn't do very much. It really, really doesn't do very much. The very first thing that we're doing here is I'm trying to take the address of where the main function is. The main function ought to be code. I think we can all agree on that, yes? The main function ought to be code. The main function ought to be somewhere in the code section of my address space. And so what I'm doing here is I'm declaring a variable that's called the main address, and I'm assigning to this variable that's called main address the address of the main function itself, so &main. My expectation is that this is going to be an address that is relatively small. It's not going to be 0, but it ought to be close to the top of my address space. It ought to be close to 0 relatively. The next line here that does something is line 15. And this is where I'm trying to get an address of a variable that has been declared and initialized on the stack. A variable that has been declared on the stack is this pointer that's called main address. That's a stack allocated variable. And so my expectation is that if I take the address of that variable, it ought to be somewhere in the stack. And if I print that value out, I ought to be able to see that this is somewhere relatively close to the bottom of my address space. It should be a pretty big number here that's getting printed out. And finally, on line 19 here, I'm declaring a new variable that's called heap pointer, and I'm calling malloc. I'm asking for space in the heap. And so I should get an address. I should have a value returned to me from malloc that is an address that's somewhere in the heap. After I've gotten all of these different addresses, what I'm doing is printing stuff out. I'm printing out where main is, I'm printing out where the heap is, I'm printing out where the stack is. And then I've got some assertions here that are, again, relatively showing that these are where I'm expecting them to be. So I expect that the main address must be less than the heap. It's before the heap in this address space. I'm expecting that the heap address relatively must be less than the stack. It has to be somewhere before the stack in my address space. So I'm going to pop a terminal open to the side here. And I'm going to go to this folder. I'm going to make this, and then I'm going to run addresses. And what I see as output here gives me some confidence that, yeah, the address space is generally laid out like that. It's not exactly what I was expecting. Main in my code section is at some address that starts at 625.125 something, a bunch of other stuff. That's not quite as close to 0 as I was expecting it to be, but it's up there. In terms of 64 bits of address space, that's a massive amount of address space. In terms of 64 bits of address space, 64 bits is like exabytes. It's huge. It's a giant, giant number. It's a super huge number. In terms of that address space, something that starts with 625 here, that's pretty close to the top of memory. That's quite close to the top of memory. My heap has a similar prefix to what my main function had. So it kind of looks like the code section is here, then the heap is somewhere beneath that. And then my stack has a number that starts with 7FF, which again is super big, and that's getting much, much closer to the bottom. The bottom, my expectation here is that this would just all be Fs ultimately. So that's the biggest number that I could possibly have, but we can assume that there's some other stuff that's going on here in terms of where the stack might be located. I'm going to hit enter to exit, and then I'm going to run this again. What I want to see with this, now that I've run this program, is, I'm going to come back to this in a second. I want to look at what the OS is telling me it has allocated for the virtual address space for this process. On Linux, there's this proc file system. We've looked at this a couple of times before. We even briefly looked at this maps file once. But let's take a look at it again, and I want to compare it to what we're seeing as output from this program. So I'm going to pop back to my terminal here. I'm going to run less proc, and then the process ID here is 1751947, and then I want to take a look at the file that's called maps here. I'm going to zoom in on this side, and I'm going to make the text a little smaller just so we can see it clearly all on one screen. And I'm going to zoom back in again so that we can actually see what the numbers are here. But what this is showing us is approximately the address space of this process that's running right now. At the very top here, you can see that there's this entire path here, home F Bristow, comp 3430, examples, lecture 21, virtual memory addresses. That's the name of the program that I asked my operating system to run. And we can see that there's like 5 entries here, and each of these 5 entries is in some region that's starting with this prefix 6514F4. In this column, and this is the one that we looked at briefly before, there's different parts of this that have been allocated such that they are read-only. So there's some part of this file that's been allocated into this address space so that it's read-only. You can't execute it and you can't write to it. Then there's a little segment here that's been marked as read and execute. So that's at offset 1000 into the file itself. At offset 1000 into the file itself, these are the instructions for the program. That's where all the instructions are for this program. So this part of memory here has been allocated. This is our code section, and it's been marked as read and execute. Then there are some more that have been allocated here that are only readable. And then there's a little bit more here that's been allocated that is read and write. So this one right here has been allocated as read and write. That's our file scope variables. They're not really on the stack. They're not really on the heap. They're kind of part of our program's code section, kind of, sort of. I need to be able to write to things that are file allocated, but I don't want to execute that stuff. That's variables. I don't want to make changes. I want to be able to make changes to it, but I don't want to be able to run it. I don't want to execute these as instructions. Beneath that, at addresses that start with 6515, we've got the heap. Literally says it right there. That's our heap right now. This is a readable and writable area in main memory. Beneath that, there's some extra stuff. This is kind of outside the scope of this course, but this is the standard library. These are all the functions that you get. Printf, fgetS. All of these functions are mapped into the address space for our process, and they're mapped into the address space of our process by kind of just stuffing them into an arbitrary looking location in memory that's after our heap. At the very bottom of this file, we've got our stack. And this is with addresses that start with 7FFFF. So these are addresses that are quite big. And so what I'm able to see with this is that the output that I get from this program is indeed consistent with what the operating system is telling me that the address space layout looks like for this process. I'm going to quit this file. I'm going to quit my pager here less. And then I'm going to run this program one more time. And then I'm going to run this program one more time. And then I'm going to run this program one more time. And I'm going to run this one more time. Do you notice anything about these addresses as I run it each time? They're changing. They're kind of like moving all over the place. I've spent an embarrassing amount of time getting this set up. Please don't ask me how much time I've spent getting this set up. This is Ubuntu. The current version of Ubuntu is 25.04. So like it was made in 2025 and it's April. It was released in April. This is Ubuntu 4.10. So this was made 20 years ago. This was released 20 years ago. This is my first Ubuntu. Not literally, but not this install, but this is the first one that I ever used. This was released in 2004 in October, I guess, in October of 2004. And the brown color scheme was a real choice. It was a real choice. I don't know why they chose that, but that's what it was. It looks honestly quite similar to what we've got. There's stuff that's missing, like I don't really have a dock anymore. I have a menu system here. But my terminal is still a terminal. It's still the same thing as I had before. Because I can't get Git installed in this, I've just retyped it. I can't get Git installed in this because there was no Git 20 years ago. There was no Git 20 years ago. And when I tried to install a package that was called Git, it was called like the GNU, I don't even remember what it stands for. It was a file manager. It wasn't version control. And so I've typed this out, and I'll ask you to just take my word for it that I've typed out the same thing, but without the comments here. But this looks approximately the same. I'm going to run a program that's called Screen. I use tmux now, but Screen is what I would have used a really long time ago. When I was working with this is also a terminal multiplexer. This would also be installed on Aviary. I don't like it as much because you have to do things like do a split and then go to the split terminal and then tell it that you want it to launch a shell as opposed to just having it work automatically. It's kind of messy. But I'm going to make addresses. and I'm going to run addresses. And then I'm going to hit enter, and I'm going to run addresses, and I'm going to hit enter, and I'm going to run addresses, and I'm going to hit enter, and I'm going to run addresses. What do you notice about these addresses each time I run this program? They're the same. Thank you for shouting. Yeah, they're the same. They're exactly the same every time I run it. And I'm even going to go to taking a look at proc 7052 maps. This file is substantially smaller than what we were looking at. There's a lot less going on in this file, but we can still see that we have a code segment that's been allocated at the top, and a bunch of it is read and execute. Then we have another segment here that's part of our code section that's been allocated as read and write. Beneath that, what we have is the heap. This is the heap. It's not marked as the heap right now, but that is the heap part of memory. Then we've got a loader here. This is related to having those functions. And then we've got libc appearing after that. And then at the very bottom here, what we've got at BFF is our stack at the very bottom of our address space. I had to go way, way back to this version of Ubuntu and this version of Linux, the Linux kernel itself, to have something that would produce output that is the same each time we do this. What we're seeing in action when we're working with a modern version of Linux is a thing that's called address space layout randomization. This is ASLR. The idea here is that I want to be able to take different parts of my address space, and for every process, I'm going to put the code section in a slightly different area. And I'm going to put the heap in a slightly different area, and I'm going to put the stack in a slightly different area. And the goal here is that if someone is able to add something to your code that causes different paths of execution to be taken, they can't predict where the code section is. They're not going to be able to manipulate stuff in such a way that it's going to change the stack pointer to be a different place. They're not going to be able to change things in such a way that they'll know where the stack even is before they start writing the code to start manipulating your stuff. Yeah. Couldn't they just take a look at proc maps? They can't, because part of this is that they're going to be doing this using stuff like buffer overflow exploits. So like they're going to go past the end of your array. They're going to write stuff past the end of your array such that they're changing the return address from the function that you're currently in. But if they don't know where the code section is in the first place, they're not going to be able to set that correct value in that return address. So they can't look at that file. They could if they had root on your system, but at that point you're already kind of like compromised. So it doesn't make a difference. So that's fair. Couldn't they just look at that file? Couldn't they just ask the question, what is my stack located at? But they can't because they don't have control of the system right now. Yeah. All right. Okay. So one last look at Ubuntu here. Just because this is like slightly nostalgic for me to be able to see this. But again, that brown was just a real, it was a choice. I don't know what was going on in the early 2000s, but yeah, here we are. I'm sure that in 20 years, we'll all be saying that liquid glass was a terrible mistake, and I don't know why they would do that, but so we've got these virtual address spaces, but the problem with our virtual address space, we just saw it, it's huge. Like if I took the difference of the code section at the top and the stack at the bottom, Well, I have 32 gigabytes of memory in this machine, and that's a lot for a laptop. That's way bigger than 32 gigabytes of address space. There's way more virtual address spaces that my process is able to address than I physically have on my machine. And so how do you take something that is much bigger than the space that we want to put it in and actually fit it into that space? How do I take this really big thing and put it into that tiny space? The first idea is described in our textbook, and this idea is called base and bounds. And the idea here is, rather than have this mega supersize address space that's 64 bits in size, let's just make address spaces much smaller. Let's make them so small that they are smaller than physical memory. If I have 32 gigabytes in my machine here, let's just say that instead of having exabytes worth of virtual address space, every process just gets 256 megabytes of address space. That's the address space that it's able to fit into. And if I take a look at this program that we've got here, that's called addresses.c, 100% this takes less than 256 megabytes worth of memory. There's no way that this could take any more than a few kilobytes worth of memory. So fair enough, this seems like an okay idea to take our physical memory and break it into smaller pieces and just make our address spaces fit into that size. Let's visualize this. So what I want to effectively be able to do here is I want to take our virtual address space, and I kind of want to take that and cram it into physical memory. So what I'm going to draw here is in the middle of this diagram, I'm going to put our virtual address space. Our virtual address space looks like what we normally think it looks like. We've confirmed that now twice, once from the side of the process and once from the side of the operating system. So I'm going to draw this out as a great big box, as we normally do. And inside this box, I'm going to put my code section, my heap section, and then at the very bottom here, I'm going to put my stack. I'm going to take this virtual address space that we've got here, and I'm going to label it this way. At the very top, this is address 0. This is 0 megabytes into our virtual address space. And at the very bottom, we're going to have 256. So this is going to be all Fs up to whatever address 256 megabytes would be, 256 million units into this address space that we've got. The idea with base and bounds is that I'm going to take physical memory, so we've reduced the overall size of our address space here down to fit into a much smaller size. And now I'm going to take physical memory, and I'm going to say that with physical memory, what I've got here is another great big box. And the physical addresses that I have in memory here are going to be, let's say that this is 0 gigabytes, and this goes all the way up to 1 gigabyte. I'm going to take physical memory, and I'm going to partition it. I've made the address space much, much smaller. And so now what I'm going to do is take physical memory, and I'm going to break physical memory into 4 fixed size chunks. in spot 0, I'm going to have addresses, physical addresses, that are 0 megabytes up to 256. In spot 1, it will be addresses 256 up to 512. In spot 2, it's going to be addresses up to 768. And then at spot 3, these are addresses all the way up to 1 gigabyte. And what we've done with our virtual address space, we made it much, much smaller. And we said, you're just going to be able to be put into one of these locations here. From an operating system perspective, my job here is to keep track of which parts of physical memory are allocated, so which are currently being used by processes. Because these are fixed size chunks, every one of them is exactly the same size, I could use something like an allocation structure. I could use an allocation bitmap to say that one of these is free, so I can use that one to put this process's memory into. This one is not free, so it's being used by somebody else. Here, what I really want to be able to say is that I want to take this entire address space and I want to jam that entire address space into one of these spots. So we're going to say that this process has process ID 1, and we're going to put its entire address space into slot 1 here. So within here, we're going to have code section at the top. We're going to have a heap. And we're going to have a stack at the very bottom. On the OS side of things, we're going to have to tell the hardware that this process is living in this location. The way that we tell the hardware that this process and all of its addresses, so everything that it refers to, the program counter, the operands and instructions and memory locations, they're all going to be relative to this address. This is a value that in the OS side, we're going to have to set as the base register. This will be in our process control block for this process. All addresses, when I'm looking up or translating address 0 for process 1, it should be plus 256 to get it into physical memory, to get to the physical memory location for where this thing is located. When I have a stack here that's located at address FFFFFF, something up to somewhere close to 256 megabytes, I should add 256 to that because in physical memory, it's pretty close to 512, or it is 512 in this case. So it's getting right close to that edge here. So the base part of this is the offset in physical memory where this process lives. And the bounds part is going to be, this is how big this partition of physical memory is. Partitioning physical memory here is accomplished in a kind of, I think this is kind of cool. I think this is kind of a cool way to do this. Partitioning physical memory here is accomplished effectively by taking these values and these values themselves are the prefixes of physical addresses. Whoops. Physical. So everything that's in segment 0 up there, all of the addresses in that partition start with 00. That's the two most significant bits. Everything in physical addresses in partition 1 here, the two most significant bits are 0 and 1. Everything in partition 2, the two most significant bits are 1 and 0. And in partition 3, the two most significant bits are 1 and 1. And so we can use these two bits to partition our physical memory and then use those as identifiers for the base register here to kind of say that this is how much of an offset you should be applying to these different virtual addresses that we get from this process. Is this okay with everybody? Okay. There's kind of a problem here. One problem is that our operating system has to live somewhere, and it's just going to have to take an entire segment by itself. It's going to have to use a whole partition here to say that this is where I live. This is where my code is. Another problem is that once I've partitioned memory, that's it. I have a fixed number of partitions here. I'm using the top n bits to say that this is how many partitions of physical memory I have. If I'm using the top 2 bits, that means that one of them gets taken for the OS, and I can run 3 more processes on top of that, because I need to allocate 3 whole virtual address spaces for those processes. If I use the top 4 bits, it's a little better, because now I get 16 minus 1 for our operating system at the top, but it's fixed. I can't run more than 16 processes at a time because I have to allocate their entire physical address space or their entire virtual address space into each one of these partitions. Another problem that we've got with this is that this part here, in between our code and our heap section, or in between our heap and our stack section, it has been allocated. I'm going to come back to this in a second, but the heap for this program that I've written here, in theory, is 1 byte. And the stack is, I don't know, this is maybe 4 bytes and 4 bytes and 4 bytes. There's not much stuff that's actually being used by this process. But with this idea of base and bounds, I've had to allocate its entire address space into this partition of physical memory. And if I've allocated this entire address space into physical memory, that big chunk that's in between the heap and the stack is not something that I can use for other stuff. It's effectively wasted memory. I can't use it for anything else. It has been allocated to a process, and it is not usable by any other processes. It's not used by that process, and it's not usable by any other processes. This is an idea here that's called internal fragmentation. This was a problem with our file system. We allocated a file to a block or a cluster, but if that file is only 3 bytes in size, we've got an entire rest of the cluster that's not actually usable by any other file because we allocate an entire cluster or block to a file. Here, we're allocating an entire partition to a process, even if we're only using a tiny fraction of the actual space that we're using here. It's the same problem across both of these different domains that we were thinking about at different levels of that memory hierarchy. Are there any questions about this? Okay. So base and bounds is kind of like a little bit laughably not a plausible way to do this anymore. On my system right now, I'm going to count the number of lines here. I have hundreds of processes running. If you're on Windows, you do Control-Alt-Delete and bring up the task manager. You can see how many tasks are currently running on your system. It's a lot more than 4. It's a lot more than 16. And every process that's running on this system has a much bigger address space than we are allocating with base and bounds. And so for a long time, I said, I don't think that this is a reasonable thing to do. But I actually think that it's getting to be a little more plausible here. So this is the Dell website. And you can call me a nerd if you want, but I used to come and do this stuff for fun. I don't know, like just configure these things to max them completely out and just see how much they cost. And so I'm adding 64 gigabyte DIMMs, 64 gigabyte sticks of memory to this machine. And I'm going to get lost every time I do it. But at 4 sticks, we were at 256 gigabytes. I'm going to get lost every time it does it. I don't know why. Dell, if anybody's watching this, let me type in here instead of just clicking the up arrow. So at 4, we are at 256. At 8, we're at 512 gigabytes. And I'm not going to keep clicking through this because it's going to take too long. And I'm going to ask you politely to take my word for this. But we can get this machine up to about 16 terabytes of physical memory, which is absurd. It's such an overwhelmingly big number. Like, you know, hard drives are 16 terabytes in size. And now we're talking about physical memory that's 16 terabytes in size. And you can see that as I'm adding these, they're a couple $1,000s each. And to get to 16 terabytes of physical memory, we've got to have a lot of sticks of RAM to put in this machine. But at 16 terabytes of physical memory, we're going to say that that is, I'm going to go down to basic here, that is 16 terabytes. I'm going to divide that by, let's say that we want to allocate 8 gigabytes. So I'm going to say 16 terabytes times 1024, that's gigabytes. So that's 16,000 gigabytes of space. And if I were to give every process 8 gigabytes of space, we could run a couple thousand processes on this machine if we just gave it that entire 8 gigabytes of physical memory for itself to run in. And it's suddenly becoming more realistic to just give every process an entire address space that's 8 gigabytes in size, as long as you have a couple $100,000 to buy a machine with. And I think that's pretty cool because that would simplify a lot of the stuff that we're about to talk about, trying to fit lots of big address spaces into a smaller thing. Thank you for humoring me on this digression. This is a little bit of old man Franklin saying, wow, look at memory these days. It's so much bigger than when I was a kid. The first computer that I had 128 megabytes of memory in it and Windows 98. And now we can put Windows 11 and then run like thousands of instances of Chrome all at the same time. So that's base and bounds, but the big problem that we've got with this is ultimately internal fragmentation, fixed number of processes and internal fragmentation. We've got these large chunks of unused memory that's been allocated inside blocks, and those blocks are likely never going to actually use that space that's been allocated to them. Even if we could have 8 gigabyte address spaces on these 16 terabyte memory machines, that's going to be huge chunks of memory here that are not being used for anything. They will be allocated for this process that we've got here that's using literal bytes of memory, and it's not ever going to actually use that. So taking all of those different pieces together and putting them back into one big free space might be enough to fit another or many more entire address spaces. And so the solution to that is to use an approach called segmentation. So base and bounds, the idea is we're partitioning physical memory. Segmentation is going to try to solve the problem of internal fragmentation in physical memory by, instead of partitioning physical memory, we're going to partition virtual address spaces. We're going to partition our virtual address space, and then we're just not going to allocate the parts of the address space that we're not actually using in this process. So I'm only going to allocate parts of that virtual address space that I'm actually using in the process. And we're going to use the word segments to describe these partitions of the virtual address space. We're not going to fix the size of the segments in memory. So while the partition of our virtual address space is fixed in size, we're going to use the same approach as we did with base and bounds by using the top n bits to represent different parts of our virtual address space. The difference is that when we actually take this segment and put it into physical memory, we're only going to allocate in physical memory as much as is currently used by that process. So let's go back to our diagram and take a look at what this might look like in the same kind of context here. With segmentation, we're going to start with the virtual address space that we've got in the middle here. But the way that we're going to partition our virtual address space here, and the way that we're going to mark up our virtual address space's range, is that we're going to say that addresses here will still start at the top at 0. So we'll still have a virtual address that's 0. But the difference now is going to be that we're going to have 64 bits of gigabytes at the very bottom of our address space. So we're going to have the entire thing. Our process, as far as it's concerned, will think that it has access to 64 bits of address space, exabytes of space. We're going to take our virtual address space and we're going to partition it. We're going to partition it in such a way that, and I'm going to draw double lines around this. In such a way that we have a code segment. The code segment is going to be segment 0. We're going to have a heap segment. The heap segment is segment 1. We're going to have a question mark, question mark, question mark segment that is segment 2. And we're going to have a stack segment that is segment 3. Modern systems actually simplify this even further. We don't have 4 segments, we just have 2 segments. We have the code heap segment and we have the stack segment at the bottom. We can simplify this to just 2 segments instead of 4 because the code size never changes. Once you put the code into that spot in memory, it's never going to grow. You're not adding more code to your program after you've started it. It's there. It's been compiled. You load it into memory. These are the instructions for the program. They're never going to change. The heap will grow in size downwards, and the stack will grow in size upwards, and they will try to meet in the center. But having 2 segments instead of 3 solves this problem of having this question mark, question mark, question mark segment in the middle. So we're going to have these different segments. And within each of these segments, our code segment in reality is only actually going to use maybe this much space. And our heap segment, it's going to grow over time, but initially, maybe it's only going to use this much space. And our stack, again, it will grow over time, but initially it may only use this much space. So it's only using some small part of the segment that we've taken from this virtual address space. And our operating system now is going to be able to say, I've got physical memory here. Our physical memory is going to be structured in this traditional rectangle shape. I'm going to have, let's say that this is in fact my laptop, 32 gigabytes of physical memory in this machine, and every process has exabytes of space in its virtual address space. But we've partitioned this virtual address space, and within those partitions, those segments that we've got here, the process that's running only uses a tiny fraction of the partition. And so rather than allocating the entire part that we've got, the entire partition that we've got for this part of the address space, I'm just going to take the part that's actually been allocated and stick it somewhere in physical memory here. I'm going to mark this as code and then :1. This is process 1 in the system that I've got right now. This means that I can take the heap and I can put it in some other location in physical memory. But I'm only going to use as much as has actually been allocated by this process. And then I'll put the stack for this process arbitrarily over here. Our operating system is going to still need to keep track of free space. It needs to know what physical parts of memory have been allocated to these virtual address spaces for the process. So which ones have actually been allocated to the segments and how much each of them have been allocated. So it's going to need to keep track of process 1 has this part of physical memory allocated. Process 1 has that part, and process 1 has that part. And there will be other processes that are also concurrently running on this system. They will all have their own address spaces broken up into small pieces and then shoved into virtual memory or into physical memory where there is enough space to put them. And our OS, I'm going to say that it also has to live somewhere. So it will live up there. For each process now, our operating system is going to have to keep track of not two things. So with base and bounds, we had the base register. This is where the virtual address space starts in physical memory, and this is how big it is. Now we have to keep track of where is the heap segment, where does it start, and how big is it right now? Where is the stack, and how big is it right now? And where is the code section, and how big is it right now? So our process control block is going to have to change slightly. Instead of having 3 sets of registers, we're going to have to keep track of the heap start or offset and size. We're going to have to keep track of the code offset or start and size. And we're going to have to keep track of the stack start or offset and its size right now. We've solved internal fragmentation. We're not allocating the space that the process is not actually using in its address space. The stack segment here is huge. addresses in a 64-bit address space that start with 1, 1, this is 62 bits of address space. That's not right. That's not right. That is right. Yes, that is right. It's 62 bits of address space. That is huge. That's a lot of space. The question mark, question mark, question mark segment is also 62 bits of address space, and that is massive. And the heap segment is 62 bits of address space, and that is also massive, and the code segment is also this giant address space size. But for this process that I've started here, while it believes that that address space is that big, I've only used 16 bytes of space for the stack. And so my stack, I'm generalizing here, it's only used some really small amount of that stack. And so we've only allocated 16 bytes of space here to represent that. For the heap, we've used exactly 1 byte. So I'm only going to allocate 1 byte worth of space here for this thing. My code section, I guess if I were to take a look at this and say how many bytes it is, I don't know why it's 18 kilobytes in size, but it's pretty small compared to 32 gigabytes of overall space. I'm only allocating 32K of space for the code section for this thing. I'm not using the whole segment, so I'm not going to allocate the entire segment. And that means that I'm not going to allocate something that my process is not actually going to use anymore. So I don't have internal fragmentation. Thinking back to file systems, this would be, we don't have fixed size clusters. Every file, if it takes 3 bytes, we only allocate 3 bytes in the file system. The rest of that space is free for other files to use as they see fit or as we need to allocate them. Here, I'm only allocating as much of each part of the segment as I'm using, so the rest of memory in my physical memory is free to be used by other processes that need to be run here. One thing that's an interesting side effect of this is I've kind of put arbitrarily my heap on top of the code section in physical memory here. And these segments are relocatable. I can kind of just put them wherever I want, wherever there is free space to put them. As an operating system, I just have to keep track of how much space is used and what is the start of this location. Is this okay with everybody? Okay, so this is cool because now we've got these processes that believe they have these giant address spaces, and we are able to put a bunch of them into physical memory, and we're kind of able to relocate parts of that address space as we see fit in this entire physical memory. I'm going to skip over this for now. And I don't want to start this yet because I want to be able to do it all in one go. And so what I'm going to say is we've solved internal fragmentation with this. Great big thumbs up. But there's a problem. There's a problem. There's a problem. Yeah. These segments that I'm allocated in physical memory for different processes are variable in size. They're not all the same size. And so I'm going to put a stack for process 2, and I'm going to put a code section here for address for process 2. If process 2 starts calling more functions, kind of recursively, we need to make our stack bigger and bigger and bigger and bigger. But when I allocated that part of physical memory for my stack for process 2, it fit. But as it gets bigger and bigger and bigger, There's not enough space there anymore. I want you to think back to Comp 2160. I know you don't want to, but I want you to think back to Comp 2160. And depending on who you took the course with, one of the assignments that you might have done was the garbage collecting memory manager. How many people did that? How many people don't want to remember doing that? The garbage collecting memory manager. This is the garbage collecting memory manager. Ultimately, I need to make a new allocation that's bigger than I currently have available. I want to allocate, let's say that this is 5 gigabytes in size right now. I want to allocate something that is 6 gigabytes. There is 6 gigabytes of free memory in this system, but it's not all contiguous. It's spread apart, different parts of this free space. So if I want to allocate 6 gigabytes of free space for some new heap, I would need to get this out of the way. The garbage collecting memory manager, if you did that assignment in Comp 2160, is we're going to stop allocations. We're going to take all the current allocations and we're just going to move them up. We're going to squish everyone close to the top. And then we've introduced another problem, which is everyone is squished right to the top. And as soon as we need to change anybody's size bigger, we need to find a different free space and move it again. So problem number 1 with segmentation is external fragmentation. I have memory that is not currently allocated to anybody, but I can't actually allocate it because the request is bigger than what I have available to me right now. So where we have internal fragmentation here with base and bounds, now we have external fragmentation with segmentation. For the records, base and bounds was an idea that came about at a time where we were coming away from you run a program and it gets the whole computer, way back in the 60s and 70s. Base and bounds comes from a time of it's going to take way too much time to fix all 3,000 programs currently in existence. We have to just make sure that they fit into this constrained worldview that we've got. And 50 years later, we're still dealing with that same problem. Segmentation was an idea that was used by Intel processors for some short period of time, but this is not actually what happens right now in modern systems. We don't actually use segmentation for this specific reason. External fragmentation is such a problem to deal with that it just makes it unreasonable to accomplish. So with base and bounds, we keep track of the base register. We keep track of the size of the partition of physical memory. This is what we configure for the processor to be able to do the address translations. We have fixed size number of processes, and we have internal fragmentation. With segmentation, we're partitioning virtual address spaces, and for each of those different parts of our virtual address space, we're keeping track effectively of a base and a bounds register. So instead of 1 base and bounds, now we have 3 sets of base and bounds registers for each of these different segments. And as this process gets switched onto the processor, we configure those different registers so that it can do the address translations for us. But now we run into this problem of external fragmentation. We're able to start many more processes than we were able to with base and bounds, but we're going to quickly have problems where there's not enough contiguous free space for us to be able to do allocations. All right, so I'm going to switch over here. We're going to take a look at segmentation fault tomorrow. And what I want to lead this in with, I'm not actually going to ask you the question on Mentimeter right now, but I want to ask you the question, and I want to let you think about this overnight, is who actually prints out the word segmentation fault? I don't want an answer right now. I'll ask you again tomorrow at the beginning of class, but who actually prints out the word segmentation fault? Who has that responsibility when you do a null dereference? At this point, you should be able to beginning to explain how a process's entire address space can be provided or supported via the concept of virtual memory. So again, base and bounds, just make the address space smaller and then we can fit it into physical memory. Segmentation, break our virtual address space, partition our virtual address space into smaller pieces, and then we can fit many more of these things into physical memory. The operating system, in terms of our course, what I care about for how the OS works with of our hardware to support this is we're configuring registers. We're telling the OS, the hardware, what it needs to do when it's, translating virtual addresses. You should be able to now start to compare and contrast these methods for address translation, so between segmentation and base and bounds. And you should have some idea of the benefits of partitioning memory and address spaces. So part of this is we're solving internal fragmentation, and then ultimately it's going to be we're trying to solve for both of those problems. That's it for today. I hope that you all have a great rest of your day, and I will see you tomorrow where we will discover who's printing out segmentation files.